Right, we'll start. That's work energy and power. Then we'll have work energy and power. Right, on work energy and power. So energy. So energy is drawn from the previous grades. So we know that energy is the ability to do work. Marar energy ability to do work. Re bolela ka elo re o nyaka maatla gore kgone go dia mmereko, but mmereko ona re bolelang ka ona ke wo. And then let's start by putting down work. Then in our physical science, we're saying this work is defined by work equals to force multiplied by the displacement, and then cos theta. Right, so re o dile moshomo ra reng re nyaka force. You must apply a force on an object, and then if ka nnete ke moshomo, then ora re force o swantse change position, and then this theta is the direction between the force and the direction. Already is the force applied, a force applied on an object, and then apply that force. When you move it, must change a position, or sometimes we just get displacement. So displacement, if we apply a force and then I move an object, then it means the work done on that object will be 0. Now what is this theta? This theta is an angle between force and the motion. So that's going to be angle between force and the motion. So require know if you apply a force on an object and the object is not moving, then it means that the work done by that force is 0. So already every force iloring apply a modima object, then it means that force swantse kgone to move the object on the from point A to point B. So already work done on an object is done by each force. So that force engwe le ngwe e di acta modima object or swantse di work. So swantse kgone to move a object from A to B. And then if you are then we'll say that the work is done on that object. So this is how we define our work. And then remember that work are now energy. Then energy ke wona matla o work and energy cannot combine ra bitsa re ba nyaka work ra ba nyaka matla le o tlo shumisha re a kgone move a object from A to B. So if matla wa ona, then we'll say 0. Then we'll come to power later, or what is it now. Given the question of work, energy and power, so you going to draw the free body diagram and the force diagram on different scenarios. Now to try to scenario jara na mo real jona or so let's differentiate between a force and a free body diagram. Then I'll come to that later, but until like a free body diagram. So a force diagram, in a force diagram, if we have an object on a surface, then the object is stationary, and then now if you're going to draw a force diagram, draw your objective and then the force exactly applying. Like for instance, if you're going to normal force, the normal force is a force exerted by the surface on the object. So it's to the surface because it's exerted by the surface, and then exert this object, then we call it normal force. And then the gravitational force is starting from the center of every object, and then it's moving downwards. So that is force done by gravity. So any other force, then it actually pull on the object. Now if we're saying free body diagram, now free body diagram, on free body diagram, if we have the same object on the surface, and then there are no other external forces than the ones that are applying here. Rather, if you want to draw a free body diagram, so I'm going to represent this object by using a dot. Then dot here the force x at this object. So a normal force and a gravitational force. So normally at this one free body diagram. So force diagram but normally question say draw free body diagram this object. Right, now let's start with our scenarios, and then or calculator more the work done, or also identify your free body diagram and the other forces that are acting and the motion. Or object guy, and then move along identify the angle between the force and the motion. So let's check the first scenario. Now if we have an object on the ground, on the surface, and maybe this object is 2 kilograms, and when it's 2 kilograms, for now the object is not moving. So let's say the object is stationary. So meaning stationary is not moving. Now this is at A and this is at B, and this is what we call delta x. Delta x, maybe we can say is 1 meters. So delta x is equals to 1 meters. Now but the object is stationary, and then if the object is stationary, is not moving, meaning let's try to calculate the work done, or let's start by free body diagram. So the free body diagram is exactly this one. So and as the object is not moving, it means for this case delta x will be 0. So let's write the free body diagram is this one. So rather we'll try to get the work done by the normal force. So let's do this. So the work done by normal force, so rename a normal force equals to the force of a normal force delta x, and then we must use cos of theta. Right, then what is the normal force? So in this case, for Newton's law, so the normal force here is the same as the gravitational force. So it means our normal force in this case will be mg, and then that is the normal force multiplied by delta x, then the cos of theta. The work done by normal force in this case, mass is 2 kilograms, and delta x, gravity acceleration is 9.8, and the delta x in this case, because we're saying the object is stationary and there's no other external force that are roaring, the delta x is 0. The object is not moving any distance. So the cos, and now because the object is not moving, so it means there is no angle between motion and the force. So it means we'll say cos of 0 degrees. So if you use your calculator, and then now you'll get a 0 joules of the work done by the normal force. So that is because the object is not moving. So again, right, that's what we can do. And then if you are looking for the work done by gravity, then obviously you'll do the same. And then now let's have the second scenario. Let's have the same object. Let's have the same object, and this one is 5 kilograms, and this is A, and B is here, and let's say delta x is 2 meters. And in this case, they're saying the object slide to the right. Objects that slide to the right, and in this case we'll say with a velocity of let's say 1.5 meters per second. Right, the object sliding that way, and for now let's say this is happening on a smoothless surface. So this is happening on a smoothless surface. Now when say smoothless surface, roaring on friction. So but the mover to the right. And then by this form, let's say the object was being pushed from this side and then going that way, and it was left to move on its own. So when it move on its own, then what is happening here? It means for that case, we'll say let's do it like this. So if we are about to draw a free body diagram for this object, so we'll say, okay, the object is moving, but at A to B there is no force that is applying on the object, and then it means we have our normal force, and Fg, which is gravitational force. And then as it is moving, there is no force that is applied. There is no frictional force, and there is no applied force from point A up to point B. So in this case, we'll say then the forces that are acting here is normal force and the gravitational force. And then now let's calculate. Let's get the formulas on how to get the normal force in this case, and then remember, some atoms want to identify the motion of the object. Now, if I draw a free body diagram here for calculating the normal force, it means I want to measure the theta. We're going to go measure a theta. So, if that is the object, now this is not the force, so this one is the motion direction. And if it's the motion of the direction or direction of motion, and normal force is this way. Now this is the force. So it's this way. It means the angle between the motion and this one is likely to be 90. So if it is 90, then the work done by normal force will be work done by normal force equals to force of normal force multiplied by delta x and then cos of theta. Now work done by normal force equals to, now we said in this case our normal force is mg and then delta x and cos of theta. Mara, I substitute for this case, but the interest is the angle between the motion and the force. So if we add substitute, we'll say mg multiplied by delta x cos. Now the angle between the motion and the force is 90 degrees. So if you check, the cos of 90 degrees is 0. So if cos of 90 is 0, then it means everything here will give us the work of 0 joules. Right, and then let's check the gravitational force in this case, the work done by gravity. So if we check out the work done by gravity, for this case, it means we'll have the work done by gravity equals to force of gravity multiplied by delta x multiplied by delta x multiplied by cos of theta. Now the work done by gravity equals to the mass times acceleration in gravity multiplied by delta x, the cos of theta. Now again, if we draw free body diagram erna in terms of motion like a force. Then the gravitational force is applied this way. This is Fg, but the motion is still going in that direction. So this is the motion, not the force. And then now the angle between the motion and the force is still 90. And what is cos 90? So the cos of 90 is 0. So it means we're saying in this case the work done by gravity will be the work done by gravity will be mg delta x multiplied by the displacement cos of 90 degrees. Now cos of 90 is 0, so in this case work done by gravity will be 0. So but there will be a case when, unless the object is moving up or down, but for now it's moving in that direction. So the same thing will happen if the object is moving to the left. So if it's moving to the left again, it means the angle between them will also be 90, because if the angle is like this one and the force is going that way, then it means the angle here is also be 90. Then it means the work done by that gravity will be 0 in that case. And that is my first scenario when there is no other external force applied. Then let's give it a try. So our level modeling, now there is an applied force on the object. Now 5 kilogram block on this, or I mean before to check out this one, let's do the one with gravity only. The same object, this one is pushed and then is sliding from A to B with delta x, and then sliding from A to B, but in this case, okay, still moving in that direction, but now this case there is a rough surface. Now if there is a rough surface, it means onale a friction, right? Let's look at it this way. Alright, now because the only friction, alright, if we draw a free body diagram, so a free body diagram will look something like this. The normal force, the frictional force, I mean the gravitational force. Now requiring the object roaring, I just push you from A to B. So the object on A to B, it move on its own. So it move ka boyona, or other external forces can't tell friction of because of the rough. Then force including again frictional force. So there are 3 forces tailoring they are on this diagram. Now again, this one again the object is going that way, so the normal force, work done by normal force, will be this one, gravity will be this one, but there is friction. Now let's add the friction. Let's start by drawing by free body diagram of motion and the force. So that is the free body diagram. Now this way is the motion of objects, and then once this motion, and then there is a frictional force. Remember, operar frictional force always opposes the motion, not the force. It opposes the motion. So if the motion is going that way, then the frictional force will go in the opposite direction. Now, if you measure the angle between these two from here to here, the angle is 180 degrees. So now, if the angle is 180 degrees, then the work done by the frictional force, we'll say work done by frictional force equals to the force of friction, and then friction actually from which point to which point. So actually from A to B, then will be delta X. So later ke work done but in opposite direction, then we'll but again the fact where the object move from A to B. So if you move A to B and there is a force applicable, or the force already available move, then it's also doing the work. So, because this one reduces the speed of the object from A to B, but there is cos theta. So the work done by the frictional force equals to the force of friction, and the force of friction in other forms, but those also from Newton's law. So but like Newton, then delta X, and then the cos. Now the angle between the motion and the force is 180 degrees. Now, or if you are calculating the force of the work done by friction force, then it means to substitute the force of friction, the displacement, and cos 180. Then you press your calculator to get. But this is the key, because we're going to substitute a formula. So if you want the correct formula, then we're going to substitute in other for you to get the answer. Right, now we're saying frictional force can be given, just a reminder from the Newton's law. They said frictional force, normally they call it Fk, or F, the static force. So but normally, because kamotla mover, then we call it the kinetic frictional force, equals to the mu multiplied by the normal force. So on other cases, normal force will be affected, but we'll revise as time goes on. Then this other way of getting the frictional force, which is the kinetic frictional force. So bakaofa the mu k, which is not having the SI units and the normal force. But formulas of normal force, they are far depending on the applied force, or applied in which way. Right, this is for a horizontal motion. Motoring, there is no other force applied, but here including friction, which means here when that was saying no other force applied, I wanna any contact force that is happening here, that is applied by the external force or the other person or the machine. Right, now scenario 1, 2, and then 3. Now on scenario number 3, there is a frictional force acting there, and then now we've covered a horizontal, a stationary object on horizontal surface. Okay, this is a stationary one, and this is moving different, and is also moving. And then the third one, a stationary object on a horizontal plane. But this is the first one of the horizontal plane, stationary. The object is moving with no other forces applied on it, and here the one. So with this one before the another scenario. So it means the work done. Let's look at this one. So we agree that the work done, when I say the work done already, is work done by each force. So there is what we call F net, and then we had something like this. So F net equals to MA. Now here it means once we can have the F net, which is the forces that are applying on the object, all of them equals to the mass times the acceleration. Then you can also recover the work net done by the forces on the object. So in this case, we have how many forces? 1, 2, 3. So if we run work net, so let's start by work net. It means equals to the work done by force 1 plus the work done by force number 2 plus ... So in that way, so it depends on how many forces depending on that object. So in this case, how many? 1, 2, 3. So we have the work net done on the object equals to the work done by normal force plus the work done by gravitational force plus the work done by frictional force. So that is our work net. So what is left to substitute? Work done by normal force, work done by frictional force, gravitational force, and work done by frictional force. But and on a horizontal it means the work done by normal force will be 0 plus the work done by frictional force will be 0 plus the work done by frictional force. So in this case, we can say work net done on this object, or on this object, or it will look at the work done by the frictional force, because frictional force is an idea the fact is that the motion and the force of normal force is 90, and the force, the angle between the gravity and the motion also 90, then they do 0 work in that case. Right, that is firstly on the horizontal part. So there is no theorem that is included yet, so I just showing how to calculate the work done on an object and the work net done on the object, not having any any theorem. So this is what we have: the formula or the definition of the work, and reminder of free body diagram, and then they are saying work done on a stationary object. Then here the work done on the smoothless surface and the work done on a rough surface. So that is to be the first part of work energy and power.